Uh, Dr. Katrina, I think after this talk, you can join.
Yes, sure.
Okay, thank you.
Thank you.
So next keynote presentation is by Dr. Thomas J. Webster from Hebei University of Technology, USA, and I invite him to deliver his talk. As we begin the presentation, let me take a moment to introduce his biography. Dr. Thomas Weber, with having high, H index, Google Scholar I-20, degrees are in chemical engineering from University of Pittsburgh and in biomedical engineering from RPI, USA. He has served as a professor at prestigious Purdue University and Brown University and in Northeastern, serving as a chemical engineering department chair from 2012 to 19, and has formed over a dozen of companies who have numerous FDA approved medical products currently improving the human health. He is currently helping those companies and serves as a professor at Hebei University of Technology, Savitha University, Vellore Institute of Technology, UFPI, and others. Dr. Webster has numerous awards including 2020 World Top 2% Scientist by Citations, that is PLOS, 2020 Scopus Highly Cited Research Top 1% in Material Science and Mixed Field, 2021 Clarivate Top 0.1% Most Influential Researcher in Pharmacology and Toxicology, 2022 Best Material Science Scientist by Citation, and is a fellow of over 8 societies. Professor Webster is a former president of US Society for Biomaterials and has over 1350 publications to his credit with over 53,000 citations. He has recently been nominated for the Nobel Prize in Chemistry. It's really, our proud privilege and opportunity to invite you, and we feel blessed if we can have some knowledge from you. Welcome, Professor Thomas. Floor is yours. Professor Thomas, please.
Hi,
Yes, Professor Thomas.
thank
Yeah.
you for the
Yes.
invitation to
Fine.
present at this conference. I really appreciate it. As you can see, I do have some academic appointments, but these days mostly I'm focused on translating what has been accomplished in my academic lab over the past 20 plus years into real commercial products. So shown on this slide are a number of different companies that I'm involved with, some of them with FDA approved implants, some of them in the progress, hopefully, of getting FDA approval, and some of them really just starting out. So, having said that, I do want to give a couple of disclosures that I will be talking about results from some of these companies that I have a financial interest in. So, I really like to start these presentations getting us all thinking about what is it we're trying to solve with our particular research program. And I have a history of developing nanoparticles, nanomaterials, and using them in many different fields. But in this particular application or presentation, I want to talk about health applications. So, of course, that brings up the question, what are we trying to solve in our healthcare system? What is wrong with our global healthcare system that needs fixing? And I guess, unfortunately, we really don't have to look very far to find what is wrong in our global healthcare system, as we are all very well aware of. Over the past 3 to 4 years, we have been suffering from a COVID pandemic. In fact, even right now, there's a recent upswing in COVID positive cases. There are numerous variants of SARS-CoV-2, the virus that has caused COVID, really wreaking havoc on our global healthcare system. And I hope I'm not being too provocative by saying viruses have been around for a long time, but our global healthcare system in 2019, and I think even today, is not able to deal with this small virus. We have seen through COVID other problems that have been highlighted, that have been exacerbated, traditional problems in our healthcare system due to COVID. Overcrowded hospitals, barriers to getting healthcare, medical devices that fail. Of course, during COVID, many medical device surgeries were paused because we were using all those resources to help fight COVID. But suffice to say, we don't have one medical device, whether you're talking about a hip implant, a pacemaker, a stent, vascular stent, neural probe, none of those have perfect 100% success rates. So clearly, we still have a problem, even with medical devices that have improved the quality of life of millions. We also have an overdependency on drugs to fix everything. All I have to say is antibiotic resistant bacteria. And you can appreciate how our healthcare system turns to drugs to solve problems and creates more problems in the process. We tend to treat every patient the same, yet we know each and every one of us has a slightly different immune system. This is why if you put the same titanium hip implant into thousands of patients, you'll get 1,000 different tissue responses. So we have to move away from this cookie cutter healthcare system and be much more tailored to the individual patient. We, of course, also have a medical system that is very reactionary. It reacts to your problems rather than predict them. No other field works this way. When you drive a car, you do preventative maintenance. When you drive over a bridge, you do preventative maintenance. So we need to be much more preventative in our healthcare system. And really the list goes on, increasing costs because of these inefficiencies, increasing number of patients because the global population is growing. It's really time for us to completely change our global healthcare system. And if none of this gets your attention, just consider that, of course, during COVID-19, the global life expectancy has decreased. The average life expectancy has decreased because of COVID. But did you know in certain parts of the world, like the United States, where I am from, life expectancy was going down before COVID, before 2019. So we can't blame all of this on COVID. There are inherent problems in our global healthcare system that need to be fixed. So as I mentioned, about 25 years ago, I turned to nanomedicine for some answers. And yes, nanomedicine, I believe, has provided some answers. The vaccine for COVID uses a liposome, which is a nanoparticle. But there are other examples that I'll give you of how nanomedicine has really helped address some of these problems. But we're not there. Clearly, we still have problems in our healthcare system that need to be solved. So clearly, what is nanotechnology? What is nanomedicine? And I think we all know by now that when I started, this was not general knowledge, but now we all know nanotechnology is really the use of these small materials, particles, fibers, tubes, nanotextured surfaces that can control cell function. And that makes it useful for their use in medicine to help prevent disease, diagnose disease, and possibly even treat disease. So while most people think of nanoparticles as the only definition of nanomedicine, there are lots of other nanostructures that exist that are helping us develop better medical solutions. And here's some of the work from our group over the past 2 decades and a half, which deal with nanostructured surfaces. So we have a history of taking medical devices off the shelf. Here you can see a spinal implant on the left. This is an amputee device on the right. We've done this for vascular grafts, polymers intended to regrow arteries. We've done this for catheters, for screws that attach orthopedic soft tissue, like ligaments, tendons, to bone. And we've done this for biodegradable materials. And our approach has really been take these medical devices off the shelf, figure out a way to put a nano texture on those materials. And what we're seeing is improved tissue response, decreased infection, and decreased inflammation. And this is all without resorting to the use of drugs. That nano texture on its own is providing the solution if you create it correctly. In fact, I'll talk a little bit more about this in a moment, but we have spun out a lot of our research into companies, and one of those companies now has over 14,000 screws in the spine that have nano textures, and there have been 0 cases of failure. No cases of infection, no cases of bone non-unions, no cases of implant loosening, no cases of chronic inflammation. And these have been implanted for the past 5 to 7 years. So these have made it to the market, and they are making a difference in our healthcare system. Now, we could spend a lot of time talking about why. Why does this research showing that nanotextures improve a tissue response, reduce infection, reduce inflammation, not just from my group, but other groups around the world who are in the same area? There are many reasons why we think this is occurring. One, of course, is a very generic reason that we find nanotextures everywhere in nature. So an insect wing has nanotextures. Those nanotextures reduce bacteria growth. We also know from biophysical models, FEM, finite element analysis, or the finite element method. We know from that analysis from work of others that a bacteria, shown here in red, when it tries to attach to an implant that has a lot of nanotextures, its membrane is too stiff. It won't fit into those contours, and if it does not attach, it won't grow on the surface and create a biofilm on the surface. In fact, if it doesn't attach, that's good news, because your immune system is more likely to clear it from the implant area. Research in my particular group has focused on surface energy. Whenever you increase the surface area of an implant, which you do through nanotexturing, you can change whether something's hydrophilic, hydrophobic, or anything in between. That change in hydrophilicity or hydrophobicity will cause proteins to interact differently. And that's important because cells depend on initial protein absorption to attach and grow. So what's shown here are AFM pictures of a nanotextured polylactic glycolic acid surface and a micron textured surface. We allowed one particular protein called fibronectin. Happens to be a great protein to improve cell attachment and tissue growth. When it adsorbed after minutes to a nanotextured surface, it adsorbed in an elongated manner. When it adsorbed to a micron surface, it adsorbed in a globular manner. This elongated manner is much more bioactive. So you can not only use nanotextures to match the absorption of a protein you want to attach, because a cell will attach to that and grow and make a tissue, or you can use it to control the bioactivity of that protein to repel a bacteria or repel an immune cell. In fact, we've created an equation, I don't have time to go into this, mathematical equation that can really predict the size of nanofeature you should put on your surface to make that implant better, to have less infection with that implant, to have less inflammation with that implant, and if it's supposed to grow tissue like bone or vascular tissue, to promote vascular or bone tissue growth. We call this nano optimized. So you give us your materials, we formed a company and a trademark, we'll figure out what the optimal nano feature is, we'll implement that onto your surface, and then we give you a stamp that it's been nano optimized to improve performance. Here's what I was talking about before. This gets to the core of why nanotextures work. Here's all the different applications we are using nanotextures in, but I wanted to show you a movie. This is the same material, the one over here that's called hydrophobic, the one over here that's called hydrophilic. These are the same exact materials. They're titanium alloys, same chemistry, only changing in nanotexture. And here you can see me putting a drop of water on the surface of one of these titanium nanotextures, and you see that it's hydrophobic. The water drop balls up. It has a very, very low surface energy. In contrast, that same exact surface, same exact chemistry, we've now created a different nanotexture that makes it hydrophilic. Change the nanotexture alone, here comes the water drop, it completely spreads. So again, What we're showing here is you can use nanotextures without changing chemistry to basically give you a surface energy that's useful for your particular application. And you obviously can use that for boats to reduce algae growth, reduce wear, windmills to reduce ice buildup, engines to reduce ice buildup, even reducing bacteria attachment on Tupperware. All of these things can be a result of nanotexturing alone and not changing that chemistry. So we've taken this idea to the FDA. And obviously the value here is that we don't have to design new chemistries. We're using the chemistries that have been implanted for decades, the titanium that's been in a hip implant for decades, the polymers that have been used as stitches for decades. Keep the chemistry the same, change only the nanotexture. This enables us to get faster FDA approval. In fact, something called the 510K approval process, which we have received FDA approval for some of these devices I'm about to present to you within months. So the first example of us taking this nanotexturing idea to a real implant was conducted by one of my spin-out companies called Nano. And this is when I was a professor at Purdue University, where we took titanium, we used anodization or electrochemistry to apply a voltage when that titanium was placed in an electrolyte solution, apply a voltage over a certain time, and we create nano textures on orthopedic screws. So we can control this very precisely depending on the voltage, the time, the electrolyte solution, many things you can change to give you an exact nano feature. We really wanted to test this idea out. So many, many years ago, we used an amputee rat model. What we did was resected the leg of the rat, inserted one of these screws, actually several, because we repeated this experiment in triplicate and 3 times. So that screw was basically anodized to have nano textures. All of that wonderful change of surface energy that I talked about, change in initial protein absorption. We figured all that out ahead of time, so we knew exactly what type of nano feature to put on this screw. We inserted it into the remaining limb of the rat, and then we looked to see how well did this grow into bone, how well did it grow into soft tissue, and did it allow skin to close the wound so that it was not open for constant bacteria infiltration. And keep in mind, these amputee models are not easy. If you know of anyone who's an amputee and has an amputee device, this is called an osseo-integrated approach, where the screw goes into bone and then you fit on top of that a carbon-based prosthetic. The remaining limb is fit on top of this. So this has to be stable in order for that prosthetic to work effectively. And that's one of the things many people complain about who have these devices, is that this screw becomes loose and it's actually never strongly attached in the first place. So after anodizing these screws for creating a nano texture, we did see qualitatively the rat walk after 3 days. Without anodization, the rat was not walking after 28 days, which is as long as we took this study. We took visual images, pictures of the exit wound. So here's the screw that's coming out of the remaining limb in the rat, and you can see the screws that are used today. The implant wound did not close. It did not heal. So this is what I was talking about. If you have an open wound where these osseo-integrated screws are coming out of, that's an opportunity for bacteria to colonize the screw, infect bone, infect the animal. It's also an opportunity for inflammation, all events that will keep this implant from attaching to bone. But when we anodized our screw, we saw the wound close. And we saw strong bone growth, which is why the rat was able to walk on this screw after just 3 days. So as I mentioned, the company Nano is now commercializing this. They went through the FDA approval process, got quick FDA approval, and it's now being implanted in over 14,000 humans, and there have been 0 cases. They are implanting this and commercializing this as a pedicle screw. This is in the spine. So here's a human x-ray with these screws that have been nano-textured to improve bone growth. And again, it's amazing to me, there have been no cases of infection without releasing an antibiotic from these implants or doing anything other than have that nanotexture. There's no extensive inflammation, soft tissue formation. There's no loosening that is occurring with these implants. it's 0 cases of failure. So this is a wonderful sign of how nanotechnology is actually helping human health right now, today. We're not waiting for this to happen. It's happening right now. Let me give you a second example, and this has to do with silicon nitride, a different chemistry. Those screws that I just mentioned were made out of titanium. So here's silicon nitride, and this is being commercialized by a company called Syntex. Syntex has a smooth, at the time, had a smooth silicon nitride material, again, used for the spine. We created a way to nano texture that implant, nano roughen it. We then implanted this with bacteria into the skulls of rats. We had a couple of controls, titanium and PEEK. PEEK is polyether ether ketone, a very popular polymer that's used in the spine, approved by the FDA. And what we saw was the same exact promise that I just mentioned. When, again, we pre-seeded bacteria onto these samples, put them into the skulls of rats, we took histology sections in yellow on these slides are bacteria. The dark color is bone. So you can see clearly with our controls, titanium, we had bacteria after 3 months of implantation into the rat calvaria or the rat skull. After 3 months, PEEK did awful. There's tons of bacteria that were present around that implant, but just simply changing to the silicon nitride chemistry, we did better. So by changing chemistry to silicon nitride, there was less bacteria. In fact, we quantified about 10% of bacteria was on the surface, but there were large gaps of new bone growth. When nanotexturing that silicon nitride, we were able to get the best response. We didn't find any bacteria after 3 months surrounding the nano rough silicon nitride. And in contrast, we found about 41% of the surface was covered with bone. So again, similar story, over 4,000 of these have been implanted, again, as a spinal implant, and there have been 0 cases of failure. So a second example with a different chemistry showing similar promise. The last example I'll give you before going into some nanoparticle and therefore laser type approaches is work we did with a company called Tiber Medical. We developed with them electrophoretic deposition. So they had screws. Again, these were screws not used in the spine, but used in the foot for diabetic patients who have a lot of neuropathy and they break bones very easily in their feet. So Tiber is commercializing these screws that can be used in the foot. Here's electrophoretic deposition. You have your titanium anode and you apply a voltage and you're basically able to coat that screw, that titanium screw, with calcium phosphate. So calcium phosphate's attractive for orthopedic applications because your bones are made up of calcium phosphate. So by coating an implant with calcium phosphate, you would think bone cells would recognize it in a more favorable way and grow bone. So we were able to use electrophoretic deposition, as just described, to coat surfaces of titanium screws with larger calcium phosphate nanoparticles in A, 170 nanometer diameter, B, 150 nanometer diameter, C, 130, and then D, 110. We compared that to plasma sprayed. This is what's done in industry today. You apply high heat and you get that calcium phosphate coating on titanium. Of course, high heat does not render itself friendly towards nanostructures and can fuse together all of these nanoparticles you might start with into micron particles. And of course, we compared it to plain titanium. So what's happening here, of course, is as we go from A to D, the particle size of calcium phosphate's decreasing. That's creating more nano texture. So when we put bacteria onto these surfaces, we see reduced Staphylococcus aureus, a bacteria that infects implants. It decreases on these smaller nanoparticle, more nano-textured surfaces. We're able to, without using antibiotics, as all of these projects, we're able to decrease Staph aureus colonization through the use of more nanotextures of calcium phosphate. Same thing with Pseudomonas aeruginosa. We're able to decrease that colonization by simply creating more nanotexture, smaller particle sizes of calcium phosphate. And the same with drug-resistant bacteria like ampicillin-resistant E. coli. Significant reduction compared to plasma spray when using the more nanotextured surface. So similar with the theme, this has been approved by the FDA. There are in over 15,000 that are implanted into the feet of patients. And again, 0 cases of failure. So I love this research. Nanotexturing is easy. It's a way to quickly help patients today rather than waiting for new chemistries to be developed and lengthy regulatory approval processes. But I do want to criticize, in the remaining slides that I have, this approach of nanotexturing. So the first criticism I'll make is that these nanotextures, everything I showed you so far, are not made from biodegradable or environmentally friendly chemistries. And every other field, whether it's consumer goods, automobiles, energy like solar panels, every other field has moved towards helping the environment while accomplishing that application, except biomaterials and medical devices. We're still using stainless steel. We're still using titanium. We're still using polymers, and none of these materials are friendly to the environment. In fact, many people have written about this, including myself, where the contribution of biomaterials to global warming is extensive. Yet we all seem to forget about it and say we're helping human health, so that makes it okay if we're ruining the environment in the process. I could not disagree more. Clearly, if you are ruining the environment, eventually you're going to ruin human health. So think about all of the biomaterials that are used today. Again, titanium, stainless steel, polymers like polyvinyl chloride, polyethylene, polystyrene. All of these leave a large carbon footprint when we make them. Our in vitro testing, petri dishes, pipettes, all of these things are full of polymers that are not recycled and again, end up in a landfill, which end up polluting the environment. So the prediction is not good. As we use more biomaterials, as we use more plastics and polymers, the contribution to global warming is going to get worse. In fact, one statistic that I find super alarming is in 2019, it was estimated that there was about 850 million metric tons of greenhouse gases produced from making polymers. This is expected to go up to 2.8 gigatons of CO2 greenhouse gas by 2050. And in fact, no region of the world is immune to this. All regions of the world make polymers for biomaterials. All different parts of the body use polymers, whether it's orthopedics, cardiology, wound care. So every part of the body is part of the problem as well as everywhere in the world. In fact, if you look at this market snapshot, the use of polymers is going to go up, obviously, in the years to come. And some of the biggest companies who contribute to manufacturing polymers for the body as biomaterials are, in fact, medical device companies. So we really need to turn the page here, and we need to think about how we can create environmentally friendly materials while helping human health. So I think nanomaterials could be the solution. I also think using lasers could be the solution to help make nanoparticles. So I do think nanomaterials, nanoparticles can help save the environment. In short, as we all know, you need less nanomaterials to achieve the same properties as conventional or micron materials. Same strength, same catalytic properties, same optical properties, same electrical properties, same magnetic. So if you need less of a material to achieve the same properties, then yes, that helps save the environment. You have to make less and you're using less. But in particular, let me focus this on lasers, since this is a laser conference, and tell you how we're using lasers as an alternative towards how nanoparticles are made conventionally. So conventional nanoparticle synthesis, as we all know, usually involves mixing two chemicals together. Maybe you put a catalyst in there, but there's a lot of hazardous chemicals. This slide shows you a lot of the hazardous chemicals used in nanoparticle synthesis. We need to get away from that. This conventional chemical precipitation of things like gold, silver, all of those types of materials. So I wanted to describe to you how we're using lasers as really this top-down approach to take a bulk material, use a laser to etch it away until you get a nanoparticle. And we've been working with Dr. Gregory Goosebears, who's from the University of Arkansas, on making these. He has been making these. We've been testing their biological properties, and we're finding that yes, you can use a laser to etch away and make nanoparticles, but most importantly, these particles are better at killing bacteria than those that are made through conventional means. So here's some results on pulsed laser ablation of selenium nanoparticles. Selenium is part of our natural diet. You can see some pictures right here where they've been created through laser ablation, and some raw data really showing the inhibition of selenium nanoparticles made by laser to inhibit things like E. coli, Staphylococcus aureus, etc. In fact, there is in vivo data we have using nanoparticles of selenium. We coated screws. These were placed in the femurs of rats, and we were able to see a statistical decrease in things like MRSA, a very prominent antibiotic-resistant bacteria, on the surfaces that were coated with selenium. And in fact, a little distance away from the implant, we also saw a reduction in bacteria. Same with MRSA, methicillin-resistant Staphylococcus epidermidis, where we see statistically changed reduction without using antibiotics, but using these selenium nanoparticles precipitated on the screws. So I think I'm going to skip this part, but we're also not only using a laser to make nanoparticles, but we're also using cells to make nanoparticles, again, as a way to get away from using these hazardous catalysts and these hazardous chemicals. So quite simply, our approach has been take bacteria, add a metal salt, and you can create, again, selenium or other chemistries very easily. And those chemistries, these nanoparticles made by cells, are better at killing bacteria. They're more safe. They're better at growing bone than those that are made through conventional hazardous methods. So let me, there's just a couple of minutes I have left, skip up to here, because this is another big criticism for that nanotexturing work that I talked about before. I think in 10 years from now, I hope we don't have a community that's simply changing surface roughness or simply changing chemistry of an implant. But we need to revamp thinking the whole medical device field and really develop materials that are much more proactive in seeing if they're working, reducing infection, reducing inflammation, and not making these implants that just react to your body. So let me give you a couple of examples of that. This first one is for sensors, where we're developing materials that you can put in the body to actually determine how well your implant is doing. And as I mentioned in the beginning, this gets us towards healthcare at home. If there's one thing COVID taught us, is hospitals like this become easily overrun, and they run into lots of healthcare issues when you have to go to one place for healthcare. So we're moving beyond this, and we're really empowering the patient and enabling them to do healthcare at home. Here's just one idea that we have where we take a titanium implant, we grow a sensor off of the surface. These are carbon nanotubes. These can electrically identify what cell attaches to the implant. Further, this information can be sent to a handheld device. And lastly, we can control on demand the release of a drug to kill bacteria, to kill inflammatory cells, or to grow bone, depending on what you need for that situation. So this is an implant that responds to your immune system. And again, remember, we all have different immune systems. So the ability of this implant to respond to your immune system will ensure implant success. We have some in vivo data to support this that I don't have time to get into, but I will show you another way that we are creating sensors off of implants, and it's using atomic layer deposition. So atomic layer deposition started in California as a way to create computer chips, semiconductors. So we're doing the same thing. Take a titanium hip implant or any type of medical device, use atomic layer deposition, and grow a sensor off of the surface. Atomic layer deposition can create nanotextures. So all of the wonderful things we talked about before, nanotextures improving tissue growth, reducing infection, reducing inflammation, holds true here too. Real quick, 12-week study in a sheep. Here are the spine of a sheep. These are all the sensors we created, the ALD-coated materials. And when we use ALD to create these materials, these sensors, we see improved bone growth. So another way to create an intelligent material that responds to your immune system is through the use of atomic layer deposition. One last look at our healthcare problems in this effort to really develop intelligent materials. And it has to do with static versus dynamic implants. Most of the implants we're inserting today are static. A hip implant, for example, a vascular stent. These don't change with time. We are pioneering the idea of 4D printing. 4D printing basically is a 3D printed material. We're all familiar with the value of 3D printing, but the fourth dimension is time. So what we can do is take a 3D printed material, we add a nanoparticle to that material that responds to near infrared light, and it changes shape in the body, from outside the body, on demand, and whenever, in real time. So here's an example of some of the work we've published where we have 3D printed things like flowers, a hand, etc. We add graphene nanoparticles. Graphene responds to near infrared, it heats up, and that enables us to change the shape. And this is a project done with Dr. Liji Zhang at George Washington University. Again, same thing with a hand, 3D print a hand, add these graphene nanoparticles, expose it to near infrared, and you can control which finger will open up. So let me show you a video of this as just an example, but we have a company that's really taking this idea and exploring it for all of these applications you can see around this video. So right now we're applying a near infrared. You can see the red light there reflecting off the bottom. Shine it onto the part of the implant that you want the shape to change. And you can see that it flattens out. We can then go over to the other side and do the same thing, flatten that implant out. So of course, we think there's huge applications in treating scoliosis. Instead of receiving, half a dozen spinal rods that children receive to straighten their spine, use an implant like this that on demand can slowly straighten the spine with just one 4D printed material. Sphincters, if you suffer from acid reflux, you get a lot of acid in here, your sphincters become weak with time. So use this material to help the strength of the sphincter to keep things like acid reflux from happening. Stem cell delivery, we're using it for intervertebral discs, where you insert this into a spinal defect, cause it to swell. That increase of pressure will cause bone to grow, so it could have applications in that area too. I'm happy to report some brand new data that we just received on 4D printed materials and using near infrared lasers to enable us to shape change in an animal. The first example is a subcutaneous, where you took a material, here's our material, we bent it and then inserted it just under the back here for the rat. We exposed that material to near infrared right on the surface, very, very close. And we were able, after 15 minutes, while it was in the animal, straighten. We also did this in the muscle. So we had, again, the same implant situation. We took a curved version of the material, put it into the back, and we were able to move a little bit farther away from where the implant was, apply near infrared, and again, we were able to flatten the material, control its shape change on demand. And the third one is where we, again, had the same thing. We implanted a curved sample into the back, applied near infrared, and we were able to straighten it just a little bit further apart underneath the liver is where we excited the animal from. So basically, we're seeing in many different spots, you can shine near infrared through the animal, right directly on top of the implant, change its shape so that it does work in vivo, not just an in vitro experiment, but can work in vivo. So in closing, I hope I gave you a good idea of how lasers are being used in nanomedicine, whether it's making nanoparticles that are helpful to kill bacteria without using toxic catalysts, or whether it's using lasers and near infrared so that you have intelligent control over biomaterial shape in the body. And along the way, I think I told you a little bit about nanotexturing, how we have medical products today that are in humans decreasing, eliminating implant failure. So clearly we want to grow that effort as well. So all these things hopefully get us through a better healthcare system, a better state of medicine than where we have been over the past century. So of course I want to acknowledge these funding agencies, acknowledge the students in my lab through the years. Now I'm moving on to commercializing these effects, and I thank you for your attention.